All right, so we're looking at ideal fluids, flow rate, and continuity equation, lesson 56. So hopefully after the lesson you'll understand ideal fluids, flow rate, and continuity equation. I know that prom is tomorrow, so if y'all want to go ahead and watch the whole video today, then you won't have to watch the video tomorrow, because I'm sure that some of y'all are probably not going to come tomorrow. So that may be what y'all want to do. Go ahead and watch the whole video today, and then for those of you that are in class tomorrow, you can work on your homework, which is going to be due Monday after we come back from spring break. So that's up to y'all if you have time, but that may be what y'all want to try and do today. So for ideal fluids, thus far we have restricted our investigation of fluids to fluids that are not moving. If a fluid is not moving, they're called static fluids, and so the investigation is called fluid statics. So if you're going to take a class in college on fluids that are static fluids that are not moving, the course would be called fluid statics. The study of the relationship between moving fluids and the forces that cause the motion is called fluid dynamics. So if you have fluids that are moving and then the forces that cause that motion, that's going to be called fluid dynamics. When a fluid flows into a pipe or a river, there's going to be friction between the individual molecules of the fluid, as well as friction between the molecules of the side of the pipe or the bank of the river. So whenever you have a fluid that flows, there's always going to be friction between the molecules and the edge of whatever your container is for your fluid. So whether that be a pipe or the bank of the river or your glass as you're pouring it out of the glass, something like that. If the viscosity, that's the stickiness of the fluid, is not great and the speed of the fluid is not too great, the particles of your fluid that pass a point will follow the same path followed by every particle that passed the same point previously. So if it's not too sticky and it's not flowing too quickly, the particles are going to go in the same path. And it's called a streamline. So we call that path a streamline. So all of our particles will go in the same path. We call this type of flow streamline flow or laminar flow, and the word laminar comes from the Latin word lamina, which means thin plate. Streamlines form flow tubes, and particles do not cross the boundaries of the flow tubes. So if we have a streamline, it's going to be flowing right in here. Do you see that? It's going to flow right in there. And it's not going to cross out of that flow tube. It's going to stay in that little flow tube. And so there's an example of a laminar flow on the left, where it's going around like this is a wing of an airplane. They are close together at the top of the wing than they are at the bottom, because, and it says we'll learn this later in the book, but it says because it's closer together, that means that the speed of the fluid must be greater, and the higher speed will be accompanied by lower pressure, which will give the wing lift. And so that's why whenever they are close together, that means that the speed of your fluid or of your air or whatever it is, the speed must be greater. And so that means that you'll have a lower pressure. And that's how your airplane flies. On the right side, they get closer together as it's passed through a constriction in a pipe, for instance. That means that you have a greater speed right here and less pressure. Okay? Looking at turbulent flow, it's characterized by agitated, disorderly motion. The particles that pass a point no longer follow the same path followed by previous particles, but swirl about and form whirlpool patterns, what we call eddies. You've probably seen eddies in water before. A riptide is basically agitated, disorderly motion, turbulent flow from like the beach or whatever. That's why you don't want to go out in a riptide, because you're going to get sucked in, and it's not going in any predictable pattern. It's just whirling around. On the left, on the left, that's the airplane wing again, and there's an angle between the wing and the approaching air, and it's been increased to the point where the airflow is no longer laminar, but is turbulent. So they turned it and turned it and turned it so far that it made it not laminar anymore. And on the right, we showed turbulent flow caused by a constriction that is not as gentle as the constriction for the laminar flow figure that we just looked at. This constriction is a lot tighter, and so that's why it made it a lot more agitated in here. It made it turbulent. It says that turbulent flow is often associated with higher speeds and or a configuration that requires a rapid change in the direction of the flow of this fluid. So this right here would be higher speeds. It's constricted, so it's got a faster speed whenever it comes out of here. This one would be the rapid change in direction. It gets pushed really high up, and that's why it ends up going into agitated, disorderly motion over here. Turbulent flow is very difficult to analyze, whereas laminar flow is not as difficult to analyze. Turbulence is caused by the viscosity of the fluid. For the present, we are going to restrict our investigation of fluids to ideal fluids. So that's what we're going to look at, ideal fluids. And we have been looking at ideal everything. It just makes it a little bit easier to practice. So the flow of ideal fluid satisfies the following four conditions. One, your ideal fluid is non-viscous. That means that there are no internal friction forces between any adjacent layers of fluids. The density of the fluid is constant. This means that the fluid cannot be compressed and therefore is incompressible. The fluid motion is steady. This means that the pressure, speed, and density at any given point in the fluid do not change. And then the flow is streamlined or laminar flow. So those are the four things that you have for an ideal fluid. Now we're going to look at flow rate. An ideal fluid is not compressible, so a given mass of fluid will always occupy the same volume. That means if you take a cup of water and you put it somewhere else and you try and push it down, if it doesn't compress, then that means that it is not compressible, and it's always going to be a cup of water. No matter how you try and push it, it's never going to change the volume. We define volume flow rate to be the rate at which a fluid passes a cross-section of a container, and we designate flow rate by using the capital letter Q. And I'm pretty sure that we've already had a Q earlier in the year to represent something else. They like to do that sometimes, use the same variable to represent multiple things, but volume flow rate is going to be represented by a Q. So Q is, you can either write volume over time, or it's your V times A, the velocity, the average speed, times the area. And it's the area of a cross section here. Okay. So let's look at an example. A pump pumps fluid into a pipe at a flow rate of 80.0 cubic centimeters per second. If the diameter of the pipe at a point is 1.40 centimeters, what is the average speed of the fluid at this point? So we're going to use our formula. Now the one that we're going to want to use is the Q equals VA. And the reason we want to use that is because we're looking for the average speed. So they told us that our flow rate was 80 cubic centimeters. So we can say 80. We're looking for our V. And then we need to find the area. Now the area, that's the cross section of a pipe. Thinking back to geometry, what is going to be the cross section of the pipe? It's going to be a circle. So we're looking for the area of a circle. So area of a circle is pi and then r squared. Now we just need to figure out what our r is. They tell us the diameter is 1.4, so our r is 0.7. Now 80 equals v times 1.539. And so you divide, and your velocity will be 52.0. And then the units are centimeters per second. So that's your average speed of the fluid at that point. Looking at continuity equation, the volume flow rate is the same everywhere along a pipe, since the amount of fluid passing one cross section per unit time must be the same as that passing any other cross section per unit time. So for this to be true, the average speed of the fluid must change as the cross-sectional area of the pipe changes. So the flow rate is going to be the same. So that's going to change the speed as your area, as your pipe gets bigger or smaller. The diameter changes. So over here, you're going to have the same flow rate as you do over here. But as the area is different on this one, and the area is different here, this area is smaller, so that means it's going to have a bigger velocity. This area is bigger, so the velocity is going to be lower. So let's look at an example. 56.2. At a point in a pipe carrying a fluid, the radius of the pipe is 2 centimeters, and the average speed of the fluid is 14 centimeters per second. What is the average speed of the fluid at a point where the radius is only 1.3 centimeters? So we're going to say VA equals VA. And that's because we know that the flow rates have to be the same. So on one side, the average speed is 14. And then the area is pi times 2 squared. On the other side, we are looking for the average speed. We know the area because they told us the radius. So you end up with that formula, because the flow rates have to be the same on both sides. And so if you solve for your V, you're going to get 33 centimeters per second. And so that would be your answer there. So for your homework, it's 1 through 20, and then the curveball questions 1 through 5. You do need to have that ready to go whenever we come back from spring break. I hope you have a great spring break. Have fun at prom tomorrow. If you come tomorrow, y'all can rewatch this video, or you are free to work on your homework. But anyway, good luck.